Going to talk about the discrete time unit impulse response and unit step response of a discrete time system, and also the convolution sum representation of linear time invariant system. LTI means linear time invariant system. So first let me talk about impulse response. Okay. So when I say response, it means that output, and here impulse, it is denoted by del of n. So the definition is simple. You have a digital system, right? You apply del of n as a input. Okay, input is del of n. Whatever the output is, we will denote it by h of n. So this is called a impulse response because the input is impulse. Now if h of n is 0 for n less than 0, then the system will be causal. Okay, so how do we justify this statement? Because what we said is del of n occurs at n equals 0, right? Like this. When n equals 0, it occurs with the magnitude of 1. At n equals 0, 0, at n equals 1, 0, and so on. And this side also at n equals minus 1, 0, n equals minus 2, 0, n equals minus 3, 0, and so on. That means what? The input is applied to the discrete time system, system only when n equals 0. So therefore, when n less than 0, there is no input to the system. If there is no input to the system, then how can you expect an output, right? The input is applied only at n equals 0. Before n equals 0, that means when n is equal to minus 1 or n is equal to minus 2 or n is equal to minus 3 and so on, you are not applying any input, right? If you don't apply any input, then how do you expect an output of the system? Therefore, when h of n is equal to 0, when n less than 0 for causal system. So that is the definition we should remember. Okay. Similarly, for the same digital system, you apply the input. Now the input is u of n, unit step input. Now this time it is called a unit step response. Now the output is denoted by S of n, discrete system ds or discrete time system. And now the output is usually denoted by small s of n. So this is the unit step output, or you can also call it unit step response. Okay, the symbol S is usually reserved for the analog frequency generally. As you may recall from your previous lecture, this S is equal to sigma plus j omega, please remember. So when there is a chance of confusion, then we shall not use S of n. Okay, we shall not use S of n to denote unit step response. We may use some other notation like A of n like that. So as long as we do not come to the bridge, we will not cross it. We will keep S of n as the unit step response. So that's it about unit impulse response and unit step response. Now let us take some examples. Couple of examples. So these are very important examples. So please pay attention, because some of these examples are a little tricky, although they look very simple. The first example that I would like to consider is accumulator. Okay, so an accumulator can be of various types, like 2-3 types. Let me take the first very simple thing. Let's say y of n is equal to sigma L is equal to minus infinity to n x of L. L is going from minus infinity to n. It is an accumulator. It accumulates data. Okay. So now the question is, what is the impulse response of this accumulator? So basically what we are saying is, this is your x of n. Let's say at n equals 0, this is your value and this is your value. Like this, just I'm arbitrarily drawing some values like that. The negative side may have like this, like some arbitrary values. 1, 2, 3, 4, 5, 6, 7, 8, 9, sorry, this is minus 1, minus 2, minus 3, minus 4, and so on and so forth. Now what is y of n in this? You are adding all the values. L is equal to minus infinity to n x of L. That means what? You are adding x of minus infinity plus up to dot 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 x of minus 2 plus x of minus 1, x of 0 plus x of 1 plus up to x of let's say instead of n, let me put okay, let it be n for a while, up to x of n. Okay, this is called accumulator. You are adding all the datas. Now if you substitute y of minus 1, then you are adding from L is from minus infinity to minus 1, x of L. In this case it is going to be x of minus infinity plus dot 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 x of minus 2 plus x of minus 1, right? If you put y of 0, then summation L is equal to 0 to 0 x of L x of L, which is equal to x of minus infinity plus dot dot up to x of minus 2 plus x of minus 1 plus x of 0. Like that you can keep on write. Maybe I will write down one more expression. Let's say y of 1. Y of 1 means L is from going from minus infinity to 1. So whatever the argument is here, the same argument comes in the summation as an upper limit. Okay, so x of L, so x of minus infinity plus dot 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 plus x of minus 2 plus x of minus 1 plus x of 0 plus x of 1. This is your accumulator. Now for this accumulator, I want to find out the impulse response. So how do you find out? You take a discrete system, discrete time system. If the input is x of n, my output is y of n. That is given by summation of L is equal to minus infinity to n. Whatever the argument you put, the same argument you put here as an upper limit. Okay. Now you take the same system, same discrete time system. Now instead of x of n, you apply del of n. So, the input is del of n now. So, what is the output? Now, output is denoted by h of n. So, this again this h of n is equal to same format, L is equal to minus infinity to n. Here this is x of L, right? So, instead of x of L, you write down here as del of L. Why? In this case the input is x of n, but in the second case the input is del of n. Therefore, the input is replaced by here the del of n. Here this x of n is replaced by del of L. Okay. Therefore, your impulse response h of n for the given system is summation over L is equal to minus infinity to n del of L. Now, you substitute different values for n and you find the values. Let us say n is equal to minus 2. So, h of minus 2, this is del of minus infinity plus dot 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 plus del of minus 3 plus del of minus 2. You should stop at del of minus 2. Now, we know the value of delta n del of n from its definition. What is the definition? Del of n is equal to 1 for n is equal to 0 and 0 if n not equal to 0. Therefore, the argument should be 0, then only it has the value of 1. So, the argument is negative and non-zero. Therefore, this guy leads to 0. And here the argument is negative, therefore, this also 0. And here also the argument is negative and non-zero. So, therefore, this also 0. So, h of minus 2 is equal to 0. Now, substitute n is equal to minus 1. So, h of minus 1, again the same expression, L is equal to minus infinity to minus 1 you put minus 1 here, minus 1 here del of L. So, this is again is equal to del of minus infinity plus dot 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 del of minus 3 plus del of minus 1 plus del of, that is it, you stop at del of minus 1, right. Again the arguments are negative here, here it is negative and here also it is negative and here also it is negative. Therefore, this all terms leads to 0. So, h of minus 1 also 0. Similarly, you can find out h of minus 2, minus 4 like that, this all are zeros. Now, let us see the beauty when I take n equals to 0. Now, when equals to 0, then h of 1 is equal to sigma L goes from, L is going from minus infinity to 0 del of L. Now, it is going to be del of minus infinity plus dot 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 del of minus 3 plus del of minus 1 minus 2 plus del of minus 1 plus del of 0. Now, this term is 0, this term is 0, this term also 0 and this term also 0 except this term. Why? Because the argument is 0. Therefore, it gives the non-zero value and that non-zero value is 1. So, therefore, h of, this is 0 by the way, h of 0 equal to 1. Now, you substitute n is equal to 1, then h of 1 is equal to sigma L is equal to minus infinity to 0 del of L. Now, again if you expand this, all the terms will come negative terms plus del of minus 3 plus del of minus 2 plus del of minus 1 plus del of 0 and we stop at, again I did a mistake, I do not know, the upper limit is 1, this both should be same, here also the argument is 1 and here also the upper limit should be 1. You stop at del of 1. Okay. So, this term is 0, this one is 0, this one is 0, this also 0, but what is this? This is equal to 1. What about this? It is positive but non-zero, argument is non-zero, therefore this guy also leads to 0. So again your answer h of 1 is equal to 1. Similarly you can check n is equal to 2, n is equal to 3 and so on so forth. You will find h of 2 is equal to 1, h of 3 is equal to 1 and so on. Even let me do this guy, how it happens. H of 2 is equal to sigma L is equal to minus infinity to 2 del of L, right? So del of minus infinity plus dot 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 plus del of minus 3 plus del of minus 2 plus del of minus 1 plus del of 0 plus del of 1 plus del of 2, like this. Now if you look at here, the argument is negative, so 0. Here also the argument is non-zero and negative, 0. This also the argument is non-negative and 0 non-zero, so it is 0. This also 0, but this guy is going to give 1. And here the argument is positive but non-negative, therefore this also 0. And here also the argument is positive and non-zero. As long as the argument is non-zero, then that gives him 0 output. Okay, so there is no contribution from this all delta functions except this guy, So this is equal to again 1. So our final result is h of minus 2 is equal to 0, h of minus 1 is equal to 0, h of 0 equal to 1, h of 1 is equal to 1 and so on so forth, right. Therefore in compact form I can write as h of n is equal to 1 for n greater than or equal to 0 and n less than 0. Now don't you see from this definition that this is precisely the definition of unit step function. Definition of unit step function. Therefore h of n is equal to u of n. So this is the impulse response of a given accumulator. now let me take the another version of accumulator. Now y of n is equal to k is equal to 0 to infinity x of n minus k. Okay. So here my accumulator accumulates from n equal to 0 up to infinity. Okay, that's all the range of n. So now the question is, what is the h of n? So how do you find out this? See, you take a discrete time system. If the input is x of n, the output is y of n. What is y of n? It is given over here. Sigma k is equal to 0 to infinity x of n minus k. Take the same discrete time system and the input is now, instead of x of n, I am applying del of n. Therefore, if the input is del of n, my output is h of n, impulse response. This is a response of the system for an arbitrary input, and this one is impulse response. And this impulse response, how will you write? Same summation you put it, because you are taking the same system. K is equal to 0 to infinity. Instead of x, you put a delta here, that's all. N minus k. Now one can ask question, what is this signal? What is that? It is again precisely once again u of n, that you can prove it actually. H of n is equal to summation over the lower limit is 0 and upper limit is infinity del of n minus k. Now I substitute different values. Let's say n is equal to minus 1. So in this case, let us take 2 initially. what happens? Minus 2. So h of minus 2 is equal to summation of k is equal to 0 to infinity del of 2 minus k. Now substitute k equals 0, 1, 2, 3, 4 like that, and expand the summation. Del of 2 minus 0 is 2 plus del of k equals 1, 2 minus 1, 1 plus del of 0 plus del of 1 plus del of 2 and so on, it keep on goes. Now again this guy gives to 0, right, and this guy also, I'm sorry, this is del of yes, I'm sorry, I have done some mistake. Del of 0, when k equals 2, then 2 minus 2, 0, so del of 0. When k equals 3, del of minus 3, when k, no, minus 1, minus 1, when k equals 4, then del of minus 2 plus and so on. Okay, now this goes to 0, and here the argument is 0, so it is positive and 0, therefore this gives 1, and here negative and non-zero, so this also 0 and this also 0 and so on and so forth. Now again it is contracting somewhere. Is that correct? Okay, this is a formula del of n minus k. Okay, so it starts from k equal to 0, k equals 0. Okay, when k equals 0, this one. Okay, del of 2, del of 1, hold on 1 second, I did some mistake, let me correct the mistake. Right, now let me expand this. When k equals 0, del of 2, I'll get it fine. Then when k equals 1, then 2 minus 1, 1, I'll get it. Correct, when k equals 2, then again I'll get 2. Somewhere it is fishy, it's not getting the answer. That's a mistake I did, I'm sorry. Here I put instead of minus 2, I have put minus 2, I'm sorry. So minus 2 minus k, now I got it. Wrong, correct, right. So therefore this is now expand. Now k equals 0, then del of minus 2 plus k equals 1, then it is minus 3 plus this is k equals 0, and here k equals 1, then k equals 2 if you put, then minus 4 plus and so on, it keep on goes, it increases in the negative direction. Therefore this guy leads to 0, and this guy leads to 0, and this guy also leads to 0. Finally your answer is 0. H of minus 2 is equal to 0. Substitute n is equal to minus 1, then h of minus 1 is equal to sigma k is equal to 0 to infinity del of minus 1 minus k because n value is minus. So again expand this, you will get del of minus 1 when k equals 0, plus when k equals 1 it becomes del of minus 2 plus del of minus 3 and so on it goes. This corresponds to k equal to 0, this corresponds to k equals 1, and this corresponds k equals 2 and so on and so forth. So the sequence keep on goes. Again this rise to gives to 0 and this also 0. So the final answer is 0, h of minus 1, right. Now we substitute n equals to 0 in the expression. Now h of 0 is equal to sigma k is equal to 0 to infinity del of 0 minus k. I can write simply minus k. It is 0 minus k. You can, if you want, you can put a 0 minus k like that. It's a del of minus k. Okay, now substitute k values. So what happens? Del of 0 plus del of minus 1 plus del of minus 2 and so on. So del of 0, what is the value? 1, and this one 0 and this one 0, 1 plus 0 plus dot dot dot. Therefore the value is 1 for h of 0. Similarly you can substitute n equal to 1, then h of 1 is equal to sigma k goes from 0 to infinity del of 1 minus k, right. Now when substitute k equals 0, then you will get del of 1. When substitute k equal to 1, you will get del of 0, plus when k equals 2, then you will get del of minus 1, then del of minus 2, plus and so on and so forth. Again this guy leads to 0, this guy also leads to 0, and this guy also gives 0, and this one is 1. Therefore 0 plus 1 plus 0 plus 0 plus dot dot dot. Therefore this also 1. Like that you can substitute n equal to 2, 3 and 4 and so on and so forth. So h of minus 2 is equal to 0, h of minus 1 is equal to 0, and h of 0 equal to 1, h of 1 is equal to 1, h of 2 is equal to 1, h of 3 is equal to 1, and so on, it keep on goes. So in compact form you can write h of n is equal to 1 when n greater than or equal to 0 and 0 otherwise. That means n less than 0. So again this is precisely the definition of u of n. So the second example also, h of n is equal to u of n. Okay, so although the definitions of the two accumulators are different, the impulse response is the same. The first one, the accumulator definition is different, and in the second case the accumulator definition is different. Now let us take the third version of the same accumulator. So as I said, y of n from the example 1, y of n is sigma L is ranging from minus infinity to the present value, this upper limit, and the argument of y of n both are same, x of L. Now what I am going to do is, I am going to break this into two summations. Let us say L goes from minus infinity to minus 1, x of L plus sigma L equals 0 to n x of L, like this. Now what is this by definition? See, here the upper range is n, the same argument is here. Similarly here also this upper range is minus 1, here also I have x of L, and here also I have x of L. Therefore instead of calling y of n, I may call by y of minus 1. Why? Here I have minus 1 and here also I have minus 1. Therefore the first summation part I can replace by y of minus 1. Take the definition from this guy. Okay. plus sigma L is equal to 0 to n x of L. Like that I can write. So y of n is equal to y of minus 1 plus sigma L equals 0 to n x of L. This is my new form of accumulator. And by the way, this one is called initial condition, because let us say I am starting my system at time t equals 0. Before t equals 0, whatever there in the system, that are called initial condition. Now for the system, let us find out what is h of n, right? So you take a discrete time system ds, and if the input is x of n, the output is y of n. What is y of n? It is y of minus 1 plus sigma L equals 0 to n x of L. Now what you do, take the same system, discrete time system, instead of x of n you apply del of n. Now the output is not y of n, it is now h of n, and the only thing you should do here is replace that guy by del of L. That's all, remaining all are same. Y of minus 1 plus sigma L is equal to 0 to n del of L. Okay, therefore your h of n is going to be, so this is the initial condition of the system. So y of minus 1 plus, this is due to the application of your input. This is existing before existing output of the system before you apply the input. Before the application of del of n, and this guy is due to del of n applied to the system, right? Now let us try to find out. You substitute n is equal to, as I said, n is equal to minus 1, then n is equal to minus 2. If you substitute, then you will get, let us say, h of minus 2 is equal to y of minus 1 plus sigma L is equal to 0 to minus 2. I cannot put like this, right? It is in the positive range. So therefore the second part completely goes. So it is y of minus 1. Because the summation starts at L equals to 0. So how can I put minus 2 here? So that minus 2 is already observed here. So simply h of minus 2 is equal to y of minus 1. Even if we substitute n is equal to minus 1, then also h of minus 1 is equal to y of minus 1. Now you substitute n is equal to 0, then h of 0 equal to y of minus 1 plus sigma L equals 0 to 0 del of L. That is only one value. So y of minus 1 plus del of 0. What is del of 0? 1. Therefore h of 0 is equal to y of minus 1 plus 1. So similarly you substitute n equals 1, then h of 1 is equal to y of minus 1 plus sigma L equals 0 to 1 del of L. Expand this summation. So y of minus 1 plus del of 0 plus del of 1. Again this del of 1 becomes 0 because the argument is non-zero, and this one is equal to 1. Therefore, y of minus 1 plus 1 minus 1. This is my h of 1. Similarly, you can find out h of 2 is equal to y of minus 1 plus 1. h of 3 is equal to y of minus 1 plus 1. Therefore, in compact form, you can write h of n is equal to y of minus 1 plus 1 for n greater than or equal to 0 and 0 for n less than 0. So, you know that this is a non-linear system, right? Y of n is equal to y of minus 1 plus sigma L equals 0 to n x of L. This is a non-linear system. Why? Why? Because of the initial condition. Whenever you have some initial conditions in the system or some energy storing device which has some energy, then this non-linearity will be destroyed. Okay. Therefore, this is a non-linear system. So, non-linear systems can also have an impulse response, but the other property that we are going to discuss in a couple of minutes, okay, will not hold up. So, convolution, for example, will not hold for a non-linear system in the form that we are that we are going to discuss now. Okay. So, this is the example of non-linear system. So, non-linear system do have impulse response, but you cannot use this convolution property and all, like linearity property, time invariance property and all those things like homogeneity and additivity property and all will not be valid. Now, let us move on to LTI systems. How the output of LTI system is denoted. A very simple derivation of what is famous now as a convolution. So, we started with impulse response like del of n gives rise to h of n. Okay. So, that is del of n leads to h of n. Then you delay the sample by k units, then the output also delayed by k units, and this property is time invariance property. Time invariance property. Even if you advance the sample by k units, then also it gives output by the same amount of advancement, h of n plus k. Okay. Now, if I multiply this signal or any one signal by some number, let us say a times del of n gives rise to a times h of n. Similarly, b times del of n minus k gives rise to b times h of n minus k, and c times del of n plus k gives rise to c times h of n plus k. What are all these properties? These are called homogeneity. If the input is multiplied by a constant, then the output will also be multiplied by the same constant. Okay. So, by the same token, if I multiply some other notation, let us say x of k, let us assume this x of k is constant, some constant value, times del of n minus k, or before going that let me show you one more thing, then I will come back to this thing. Let us say I have an arbitrary signal like this, and I have 2 here, 1, 1.5, 0.5, minus 0.5. I am just drawing this figure, some arbitrary figure, 1, minus 1, minus 1, minus 1, plus 1 like this. Let me call this is x of n. Now what is this signal alone? This is x of 0. What is x of 0 here? It is equal to 2. Let me write down the value first. This is 2, this is 1, and this is 1.5, this is 0.5, and this one is minus 0.5, and this one is 1.5, and here this is 1, minus 0.5, minus 0.5, minus 0.5. This is my signal x of n. Now 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm sorry, these all are negative values, right? So minus 1, minus 2, minus 3, minus 4, minus 5, like that. Now this one is x of 1. What is x of 1? X of 1 is equal to 1. And what about this guy? X of 2. What is x of 2? 1.5. This one is x of 3. What is x of 3? 0.5. And this one is x of 5. That is 1.5, and so on and so forth, right? So as I said, del of n, it gives rise to h of n, and now similarly del of n minus k gives rise to h of n minus k. Now I multiply by some constant here. That constant can be, let's say, x of 0 times del of n, it gives rise to x of 0 times del of n, where x of 0 is a constant. What is that constant? If you look at here, x of 0 equal to 2, x of 0. So that is equal to 2. So instead of writing 2, I am writing x of 0, that's it. That is the sampled value of at that particular time instant. Okay. So similarly, x of 1 times you multiply by x of n minus 1. I did a mistake, the same mistake I am doing here also. This is h of n, and this one is going to be x of 1 times h of n minus 1. If you send x of 2 times del of n minus 2, then this is going to give x of 2 times h of n minus 2. So if I multiply the input signal del of n minus k dot 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 by x of k, by a constant x of k, then the output should be multiplied by the same constant x of k times, now the output is h of n minus k. This is the impulse response and this is the input. Okay. So this is an example of application of the principle of homogeneity. And time invariance, TIV. Okay. Now what you do, then you apply the principle of superposition. Okay, like x of 1, maybe I will write down some more samples, let us for completeness. X of minus 1 times del of n plus 1 gives rise to x of minus 1 h of n plus 1, x of minus 2 del of n plus 2 gives rise to x of minus 2, the same constant, and the impulse response is h of n plus 2, like this. Now you add all these things in the left hand side, the same thing will happen in the right hand side also, like your superposition principle. Your superposition principle says a times x1 of t plus b times x2 of t gives rise to a times y1 of t plus b times y2 of t. See, a times x1 of t individually gives a response of a times y1 of t. This individually gives a response of b times y2 of t. Now if you add the from the input side, if you add the input, and that will be equal to summation of the output. That's what I have written here. Therefore, you add all the inputs in the inputs before you give to the system, then the response will be summation of the individual responses. So this is my first individual response, second responses, third response, fourth response, fifth response. Okay, so we sum this up, we apply all these inputs simultaneously by adding it. Okay, k going from minus let me write down first. So x of minus 2 times del of n plus 2 plus x of minus 1 times del of n plus 1 plus x of 0 times del of n plus x of 1 times del of n minus 1 plus x of 2 times del of n minus 2. This all together gives rise to, see, this term x of minus 2 times del of n plus 2 gives the response like x of minus 2 h of n plus 2, right? Then this term gives output which is plus x of minus 1 h of n plus 1, right? Then this term x of 0 and del of n gives rise to x of 0 times h of n. Then this term x of 1 times del of n minus 1 gives rise to x of 1 times h of n minus 1, and then this term will give rise to x of 2, that constant, same constant, here also x of 2 and here also x of 2 multiplied by the impulse response h of n minus 2, and keep on, it goes up to infinity, this to the right hand side as well as from the left hand side it comes from minus infinity. I mean here I may have x of minus infinity and del of n plus infinity, and here it goes up to x of infinity and del of n plus infinity like this. Therefore, I can put it in the compact form, the left hand side, summation of k is equal to minus infinity to plus infinity x of k h of n, del of n minus k del of n minus k. What is the right hand side? Right hand side is also the same thing, k is equal to minus infinity to plus infinity x of k, instead of del of k here I have h of n minus k. Now recall from your previous lecture, what is this? This is the same as x of n. This I already discussed in the previous lecture, please go through. So this is nothing but x of n. This is not equal sign, it is gives rise to, I am sorry. You are applying to the system, discrete time system, ds. Input is this one and output is this one. So x of n is given to the discrete system. This one is my x of n, and the output is sigma k is equal to minus infinity to plus infinity x of k h of n minus k. Okay, and this is precisely what is called your output y of n. So the output of the discrete time system is y of n. So an arbitrary input, here x of n is not an impulse, it is an arbitrary input. arbitrary input to the system. See, an arbitrary x of n can always be expressed in this form. The output therefore must be equal to y of n, which is the famous convolutional theorem. So, for an LTI system, the output y of n is equal to summation of x of k times h of n minus k going from minus infinity to plus infinity. Now, by simple manipulations, by putting n minus k is equal to r in the above expression, one can easily show that this will be equal to summation x of n minus k and h of k, where again k goes from minus infinity to plus infinity. It is very simple to show, in this one what you do, substitute n minus k is equal to r, right. So, then what is k then? K is equal to n minus r, right. Then when k goes to minus infinity, then n goes to n minus of minus infinity, which is equal to r. Therefore, r n plus infinity is equal to r. Therefore, r goes to infinity. Therefore, when k goes to minus infinity, then r goes to infinity. That is what we mean by limits. Similarly, when k goes to plus infinity, then r goes to minus infinity, right. Now, this one becomes sigma, instead of k I have r now, r is equal to plus infinity to minus infinity, then x of k will be replaced by n minus r, and then h of n minus k is r, h of r, and this is the y of n. Now, after all, in this summation, r is a dummy variable, right, dummy variable. So, if it is dummy variable, then you can change to some other dummy variable. As I said in one of the previous lecture, that suppose you have t times dt and the limit is from 0 to 1, then this is like t square by 2 and the limit is 0 to 1, so it is 1/2. Similarly, the same integration I can write like this also, 0 to 1 tau d tau, again it will give the same answer, because after all the tau is a dummy variable. Once the integration is over, then the result is going to be 1/2. There is no either t or tau. Similarly, in this summation, this tau is a dummy variable. I can put anything else. Therefore, I can put instead of r, I can put again, bring back my old friend k. K is equal to plus infinity to minus infinity, x of n minus k and h of k, right. So, since summation like no a plus b, I can write b plus a. Therefore, the summation I can write, instead of plus infinity to minus infinity, I can write minus infinity to plus infinity, x of n minus k times h of k. This is my y of n. Okay. So, either you can write y of n as in this form, or you can write x of k times h of n minus k by simple manipulations. Both are correct. After all, r is a dummy variable here, so I can change r by k. And this convolution sum is denoted by a special symbol, star symbol. So how do you read this? X of n convolved with the h of n. So this is a symbol reserved for this. Okay, here the star stands for convolution. Okay, in this particular context, if the star is written above the symbol, like is a star like this, it represents complex conjugate. You are taking the complex conjugate operation. Okay, like if I put a h star of n, then it is a complex conjugate of h of n. Complex conjugate of h of n. Okay, if the star is written above a symbol, then it is a complex conjugate, and if star is written in the horizontal line, then it is a convolution. Okay, so obviously these two summations, let's say 1 and 2, these two summations are identical. Okay, therefore the order of convolution is not important. In other words, the convolution operation is commutative. Okay, so either you can write x of n commutative with h of n, or h of n commutative with convolved with x of n, x of n convolved with h of n, or h of n convolved with x of n. So in other words, convolution is commutative. The operation of convolution is commutative. Okay, so there are some special cases that we will encounter in practice. Okay, so in general our convolution is mind you, this applies only to LTI systems, linear time invariant systems, because we have invoked in finding the summation the principle of homogeneity. We invoked the principle of homogeneity. Then the first one is time invariance, and then homogeneity, and then superposition. Therefore the convolution formula is derived based on these three properties. So while deriving the convolution-sum, we invoked time invariance, homogeneity, and superposition. Right? The input is delayed by a certain number of samples, k samples, then the output is also delayed by the same number of samples. Like you take del of n minus k, then output also delayed by h of n minus k. So this property is called invariance, time invariance. Okay, so and then what we said, if this sample is multiplied by some number x of k, del of n minus k, then the output also will be multiplied by the same number x of k times h of n minus k. So this is homogeneity property. And now you add all these samples, like there are n number of samples. If you add, then you put the summation. So that is why superposition comes. Okay, in case if the system is time varying system, linear, but the system is time varying system, then also you may have convolution. In that case, your y of n is not going to be x of k multiplied by h of n minus k. Instead of it is h of n comma k, where k goes from minus infinity to plus infinity. Okay, so instead of h of n minus k, we put k h of n comma k. So this is for time varying case, and this kind of system output we will be studying in the wireless communication, where the channel is continuously changing. So this h of n is nothing but the channel response. When the impulse is applied, transmitted over the channel, then how the channel response is, or what is the output of the channel, that is called a channel response. Because you have a mobile phone tower, and here you put an antenna, it transmits the signal. Either the signal comes directly to you, or it may falls on some building and gets reflected to you, or it falls some moving car and again it comes to you, or it may fall some trees and again comes to you. Therefore the channel, either the objects surrounding you is changing, or you yourself moving to somewhere else. Therefore the channel is changing. So you cannot say that channel is that system is time invariant system. every second the system is changing. Therefore, the wireless channel is modeled as a time varying system. Therefore, for a time varying system, we write instead of n minus k, we write h of n comma k. Okay. So let me stop at this point. We will continue from here in the next lecture.